If you have one function bigger than the other function in an interval, then the area between those two curves is just found by taking the integral between the 2 points of the top curve minus the bottom curve. So what we're doing is we're breaking up our x-axis into little rectangles. Think about your Riemann sums. You're figuring out that area, and it always works out to be the definite integral of the top one minus the bottom. Sometimes it might make sense to do the integrals separately. Sometimes it'll make sense to put the functions together and simplify first. So we're going to look at some different examples with this. Oh, I was waiting. Good? All right. So now I've drawn the curves for you, but usually that graph wouldn't be given. I'm going to color code right now. Are you okay that I made this one blue and this one red? Does that make sense to you based on the picture? Okay. How do we know? Well, one parabola is opening up, one parabola is opening down. If we want to find the area between these two curves, that's the area we want to find. You have to know which function is on the top and which function is on the bottom. How would you do that if you didn't have the diagram shown for you? Well, I know that the blue one opens down. I know that the red one opens up. Does it make sense that the blue one has to be on top if it's two parabolas enclosing an area? So sometimes a quick little sketch can tell you that. The one that's opening down and the one that's opening up. If you're going to have an area enclosed by those two, you would know that the blue function has to be on top. Now, we have to find out, where does this start and where does it end from A to B? Well, that's where those two graphs intersect. So if we make them equal to each other and solve for x, we get x is plus or minus 2. So we know that this point is at negative 2, 2. And this point is at 2, 10. So if we want to find the area enclosed by two curves, we need to find out where they intersect. And once we've found out where they intersect, now we can use that area formula, which is just the definite integral from negative 2 to 2 of the blue one minus the red one. What was the equation of the blue one? That was the negative x squared graph. What was the equation of the red one? That was the positive x squared graph. And this would be one where I would not want to do them separate. It makes sense to put them together because certain things simplify and you've got an integral that's easy to do. If trying to simplify them meant that I couldn't do the integral, then maybe I'd like to do the integrals separate. And then from here, How easy is it to integrate an x squared, add 1 to the exponent, and divide? Personally, as far as your notes go, what's in the green box, I don't know if you need to write it down. I'm absolutely certain you could do that mental math. If you want to just maybe write out part of it, and then go dot, 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 and write 64 over 3, that could save us some time. Perfect, thank you. Some of you are super fast writers, so you're like, I can get it all down. Ready? Good. Again, if the sketch wasn't there, can you see that parabola is opening up? Then if you drew a line with a positive slope, this doesn't enclose any area how I drew it right now. The only way it would enclose an area is if the line was on top and the parabola was below. Okay? If this was the case, if we had the line underneath in the parabola, what would happen when you tried to find the intersections? You would get no solutions. It'd be like they never intersect. Well, it's hard to find the area between the two curves if they never intersect. So then you would know, once you solve your intersections, you would be like, well, the only way this is possible for them to intersect is if the line is on top and the parabola is underneath. That's important because when we're doing the area, we have to make sure that it's the top function minus the bottom function. I think this is a good time just to take a step back and be amazed at what calculus has allowed us to do. If you were trying to find that area before calculus, it'd be next to impossible. The shapes are not nice. You're like, I've only got rectangle formulas, I've got circle formulas, I've got triangle formulas. This is a parabola and a straight line. Nothing works out nicely. Probably the best you could do is take a little tiny grid paper and put it over top and count squares as an estimate. Now, all of the stuff that we've developed with all the Riemann sums and connecting it to derivatives and to integrals, this is a very complicated area to find, and now we have a technique that is, for all intents and purposes, relatively easy to calculate. You know how to simplify, you know how to find definite integrals. get an answer for that area. And since we've been able to do derivatives of every single function we've made, and for the most part, integrals of every single function that we know, we can now find any kind of area we want. Everybody good? Yes? Okay. So on this one, I want you to draw the diagram first. And I'll put the diagram up in a second. So we have to figure out which function's on top, which function's below. All right, check how you did. Did your square root graph should have been below your e to the x graph. If you're thinking about points from 0 to 1 on the blue graph, would you agree that you have 1, 1 on your green graph? You have 1, e. This point here on your green graph is 0, 0. Obviously on your square root graph, you have 0, 0. So again, having all of our basic graphs available will help us to draw the picture. The picture is important because we needed to know that e to the x was the graph on top. So now if I want to find that light blue area, it would be the integral from 0 to 1 of e to the x minus the square root of x. In this case, you can't simplify anything, so you would basically be integrating each of them separately. Do I need to separate this, write this step? No. I feel that if you went directly to this from 0 to 1 would be fine. So had you done this step, instead, you would get exactly the same answer. Does that make sense? Do you have an option? Could I integrate this all at once directly? Yes. Could I separate it and integrate it? Yes. So both of those forms would give you the same answer in the end. One is not right over the other. Okay, I'd like you to try this next one. On your own. And again, in the picture there, it doesn't matter that part of it's below the x-axis. You can just find the intersections and calculate the area. right, you want to check how you did? Intersection points were at 2 and -2. Then the area ended up being 32/3. Again, I'd like you to draw the picture first. You got your cos graph, you got your straight line, and I have the point hidden right now because I want you to think, can you solve the intersection? The intersection is when x is equal to 2 cos x. I'll tell you, the exam is going to make this question easier for you than I am. And the reason the exam is going to make this question easier for you than I am is the exam has 2 sections. It has a non-calculator section and it has a calculator section. That's a huge hint given to you. I haven't told you if you're allowed to use your calculator or not. That makes it harder. Can you solve that without a calculator? Right? You could try. Probably that's what would happen. You would start trying without a calculator and get stuck, and then be like, oh, I have to use my calculator to find this value. I should actually have 3 decimal places, but where I got the picture from had 2 decimal places. Something though, okay, something that is problematic, if you type in this exactly, it's rounded. So I'm going to go through a couple of calculator things to help you out here. First of all, if I want to find out, clear this out. So if I want to solve where is 2 cos x equal to x, I could graph it. I could graph 2 cos x on one side, x on the other side. I could draw that graph, and I could find, second, calculate number 5, the intersection, 1, 2, 3, and it solves it, and it's actually 1.0298665. Now, whenever you solve something on your calculator, if you leave that calculator screen, that's the last answer you found. So I'm going to store that as A. So I can go store alpha A, and notice the A comes up as my 1.0298. I now want to figure out this, 2 cos of x minus x. And on my calculator, I have some shortcuts. So first of all, I want to go to math, and I want to go to number 9, find my integral. Now I can go 0, and instead of having to type that in, I can go alpha A. That's really nice, because then I don't lose any marks for rounding early. It also is much quicker to type than all those decimal places. Next, in here, I could retype cos x minus x, which in this case I might do because it's not very big. It really would not take me long to type in cos x minus x. But we already typed cos x into, or 2 cos x into y1 and x into y2. So what I could do is I could just type y2, again, my alpha menu. Alpha menus across the top have that under bars. You also have it under your bars menu. So I can just go y2 minus y1. What are we differentiating with respect to? With respect to x. So when I push enter here, I get negative 1.184. That's the 3 decimal places.
Sorry for the interruption. With semester 2 Hockey Academy students, please make your way down to the bus. That's semester 2 Hockey Academy students, please make your way down to the bus.
I think you did x minus 2 of those.
Oh, I did them the wrong way. So another advantage of actually typing it in. Second, did you know this trick? Second enter retypes in everything. And then I should have done y1 minus y2. Okay, but again, we have some built-in checks. Area between two curves should be positive. Anytime you do it in the wrong order, you will get the exact same number, but negative instead of positive. So this is correct to 3 decimal places using all of the values. If you have a calculator, use the calculator. Like I would not even, technically, I'll do it nicely so if you're still copying, I would not show this step. I would not show these steps. I would directly go to my answer, put a box around it, and a smiley face. I didn't have to show much work. Perfectly fine, because it's a calculator question. Don't waste your time, because the exam is going to be, there's going to be some tough questions on it. Just like our tests, right? But the difference between your tests where you like skip English and get in trouble, or I get in trouble, right? That's not going to happen on your exam. You're not going to be able to say, I just want to skip what I'm doing for the rest of the evening and keep working on my AP exam. They're going to say, time's up. So the more places we can save time, the better. Number one way to save time, just don't make mistakes, especially on multiple choice questions. Mistakes cost you so much time on a multiple choice question, because what happens when you make a mistake? Your answer doesn't match up. You basically wasted all of that time. Now, that's easy to say, right? Okay. I learned something in math today. It's easier if you don't make mistakes. That's easier said than done something. All right. Here is our first question where find the area between the two curves, but the area between the two curves, if I take out my fancy crayons, I have this area here, which I'll color nicely in purple. And then I also have this area in here, which I colored in orange. And when we find the intersection points happen at, see it from the graph, at 0, -2, and 1. This one's actually not bad to solve without a calculator, because if you make them equal together, you can factor out the common factor of the x and solve it by factoring, and you get all 3 intersection points. But the problem, right, why can't I just go from -2 to 1? The function that is above changes. All right, so we'll finish this on up tomorrow.